So first of all, thanks for the invitation. I'm very pleased to be here today. So let me mention that this is a joint work with Jean-Baptiste Campesato and Adam Pawłowski, which are somewhere there in the physical audience. And so I want to show you say a link between the so-called Motivic Milnor fiber and the more maybe classical topological Milnor fiber, going at least at some point via a bit of log geometry. So there will be not much about log geometry in this talk probably, but anyway. So somehow I want to show a common framework linking the Motivic Milnor fiber and the topological one. So let me begin maybe with some just classics. So first for topological Milnor fibration. So let's say in this context that I will take some, say, non-singular variety, algebraic variety. Over C and some regular function in it. So polynomial function. And let me make maybe just a drawing to explain that. So I have maybe somewhere the zero set of the function. And function go to C somewhere. And say you have some small circle around, and I have some tube along the singular fiber. And then picking some point here, I have a particular fiber that will be this topological Milnor fiber. So let me maybe state the result like Milnor did. Meaning that I will not exactly state a result corresponding to this drawing, but anyway. So rather, we'll now look at a small, let's say that that's x0, some singular points in the zero fiber. Take some small sphere around this point, remove the zero locus, and go to the circle, unit circle, just by taking, say, the argument of the functions. Like the function divided by 9. So that's what the statement by Milnor that this is a locally trivial fibration. Yes, maybe this is not exactly the unit circle. Okay, we'll not say more about the topological Milnor fibration, at least in the introduction. And let me spend a little bit of time to say something about the Motivic. So, of course, to define this precisely, you need a lot of time and introduce Motivic integration, so I will not do this. I want just to give you some aspect of the definition to be able to do the comparison later. So, maybe mention that this is by Hennenfent and Loser in 98. And this produce say an algebraic object more precisely, it leaves some rotating ring that will somehow represent this topological Milnor fiber, which is a topological object. So let me be a bit more precise about that. So this object lives in some rotating ring of varieties, algebraic varieties over C. So let's just say that this is generated by isomorphism classes of algebraic variety over C, subject to, say, an additive relation if say Y is a closed immersion in X, then the class of X will be the class of Y plus the class of the complement. So you have a multiplicative law too, and somehow this is some universal ring with respect to the isomorphism class of varieties on this relation. Typically, we have a morphism from this to Z via other characteristics with compact support, and of course many others, like for example, say Hodge-Dodling polynomial in polynomial ring in two variables, constructing via mix of structure, and say some over, any additive invariant will factorize for this ring. In this ring, we have a particular class given by the class of the affine line, which play a particular role. In particular, we use to invert this class, which is a bit at least necessary for the definition of this Motivic Milnor fiber. So let me give roughly the definition. This passes for the Motivic zeta function, which is some geometric series defined more or less like this. So you take a generating series whose coefficients are some, the class in this rotating ring of some arc spaces related to the function. So let me just use this notation, which is some arc space related to n. For this function, we already encountered such arc space this morning in the talk by Nero-Budo, and with some coefficient with this L inverted. I will not explain what are these classes precisely. I will not need the definition. Let me just say that if you choose some resolution of the singularities for the function, then you have a rational expression for this, which will be of, say, the following form. So, So I pick a resolution of f. And this combinatorial data are here to describe the exceptional divisor. So given by some smooth hypersurface, normal crossing in the blowing up, I mean in the resolved varieties. And so picking a subset of this set of indices, I have here the class of some variety constructed on this resolution. I will say more about this later. And here some series constructed by such product on these data here, nu I and I are related to the resolution of the function. At this point, what is of interest for me is that this gives a rational expression, and it makes sense to make t go to infinity in this expression. So here we have the same power. So this will give a -1 term to the power cardinality of j. So this will go to the sum of the non-empty j in I to the -1 to the cardinality of j times the class of this variety. And so this is essentially this object that would be the Motivic Milnor fiber. So these classes live, at least the Motivic zeta function as coefficient in this ring. So this gives a definition for this object here. So even if we don't have L appearing or L-1 appearing there, we need it in the definition. And this gives the Motivic zeta Milnor fiber at least up to a sign. So this will be minus this limit. So leaving here. So by some result, let's say, theorem, let's say, by Hennenfent and Moser, this Milnor fiber is related to the topological Milnor fiber. For example, taking the Euler characteristic, that we have the same. So this makes sense because this is a topological object, and this makes sense because it factorizes via the containing ring. Same with Hodge-Dulling polynomial. Again, the right-hand side makes sense by this diagram. The left-hand side makes sense by construction of a mixed structure on the topological Milnor fiber. And well, for any invariant additive in the sense that it factorizes here, we can do the comparison and we obtain the same thing. So a priori, this looks quite surprising that we may have a relation between these two objects. And of course, there was some, maybe, yes, how do you prove this? Well, essentially, use a resolution of singularities. On the right-hand side, we have a formula for this. And we'll do the same on the left-hand side. Typically, from Euler characteristic, use a compo description of the Milnor fiber, and you see that the formula coincides. So it's really computation. So of course, of course I don't know, but anyway, there are now maybe new results which give some more understanding why we should have a relation between these two objects. So let me mention some of them. Of course, I needed that blackboard, but no. Let's do without. Maybe there is a button. Come back. No? No, maybe not. Okay, so let me ask two questions. First, so why do we have a relation between the topological Milnor fiber and the Motivic one? Of course, we have a result, but why should we have something like this? So there have been several types of results. Probably first one is by Niquez and Sebag. Going via non-Archimedean geometry, they construct some object, non-Archimedean object, for which we can compute the cohomology, Berkovich cohomology, and prove a comparison result between the Berkovich cohomology of this object and the cohomology of the Milnor fiber, and taking care about the monodromy too. So again, using non-Archimedean geometry, Wachowski and Loser again consider some non-Archimedean object which may give back again information about the topological Milnor fiber and the Motivic one. This uses Motivic integration developed by Wachowski-Kashtan. So it uses a lot of model theory. And maybe again some other result by Niquez on Payne more recently. Maybe, yes, I should mention this one too. So maybe again a bit in this spirit of Kashtan-Wachowski Motivic integration, they make some relation, but all these results are in non-Archimedean geometry. So one of the goals today is to give a more classical approach why it should be reasonable to have such a relation between these two objects. And a second question will be, what about these signs which appear in the formula? Yeah, so we have a minus signs which appear in front of the sum, and then some power. So this appears from the combinatorics when you take the limit when t goes to infinity. But well, we have some alternative sum of classes of algebraic variety, but this does not give you one algebraic variety, which takes care about all of these pieces, notably because we have some minus sign. And the over minus is just there in order the result works. Otherwise, you have a minus between your result here. Okay, and I wanted to use, yes. I haven't been very precise there. Is it local? Is it global? Where are the actions, monodromy action? So let me just briefly mention that we can add some action, notably taking care about the monodromy. So here we can consider the rotating ring of algebraic variety with some action, let's say action of C star. And then, I mean, in the story, your set must have some action too. And at the end, you obtain something with action here. And this action is compatible with the monodromy here. And if, I mean, in the way I will use it later, it's good also to have a relative setting here. So not simply taking variety, but variety with a morphism. So to take care about the action, it's good to have a morphism going to C star. And let's say that this will be relative to the divisor too. So it will be relative to the exceptional divisor and to C star. And so the same for this set, the same for this set, notably here we have an action and some morphism. This is maybe a bit technical to say this now, but it will appear somewhat naturally later, and really we will use this morphism too. Okay, so let me try to state. Put this back. So what will be our result? So essentially no result, or at least no new result, but a common framework to compare this object. So to state our result, we need to be already in the normal crossing situation. So we take our regular function from our non-singular complex algebraic variety. Let's say that this has only normal crossings. So the zero set, so this is some divisor, which is a finite union of non-singular hypersurfaces meeting transversally. So which is the situation after applying the resolution. And then what we do is that we construct several spaces. So let me call this here something what I will call MD mot for Motivic. That will so naturally live in some space here, which will project naturally to some other space, which will be more of topological nature. I will fill the gap later. This comes with a map induced by the function f, let's say f top going to S1. Of course, I erase a Milnor result, but this has to be thought as the topological Milnor fibration in the Milnor spirit somehow going to the circle here. Here we'll have a map again induced by F going to, let's say, C star. And we say somehow put this in some, say, complete picture. So we discuss a lot about the name, and we use complete, yes, for the complete picture. Going with some F completes to something like this. So 0 plus infinity, close at infinity, times S. So these maps are natural, in some sense. I will try to explain. I still have some time, yes. Here, we have to think about this somehow, about the real oriented blowing up of, say, C star compactified by a point at infinity and blow up this point. So we try to explain this. But yes, at least maybe it should be more precise. But yes, this will give the topological Milnor fiber, as I mentioned. Actually, this is really, depending on the construction of the object, really the Kato-Nakayama log space, constructing using log geometry, which do give a model for the topological Milnor fiber. So that's really this part. This part, I mean, this object is on algebraic variety, stratified algebraic variety, stratified with respect to this divisor. And above each piece of the stratification, this will give exactly the set L and J star appearing there. So up to this combination of sign, this object determines the Motivic Milnor fiber. So this determines, I mean, all of this determines the fiber and also the fibration, actually, more than the fiber. Okay. So yes, my goal is to explain this. Maybe you have some questions? Yes? Yes, good question. So this is algebraic, so the map will be algebraic. This is rather topological, so it will be a continuous map. And in the middle, so it's a bit mixed between both. I mean, this is not an algebraic variety of a C, nor the C's. But anyway, we have some C star inside. We'll see if it's appearing. So let's say how the construction goes. So construction of these spaces. So I will not be able to do the full construction, but let me give some more. This can be done via logarithmic geometry. Which has the advantage of making it completely functorial. Notably to give all these maps. And also it can be very useful when we want to compare. This is one model for one resolution, but if we choose another resolution, then we have to compare. And this functoriality is very useful also when we want to compare for different models. What does this give? So it's functorial. This is easy to define somehow using this logarithmic geometry, but probably we don't really understand what's going on just by the definition, but at least it is easy to define. So that's nice. And as I mentioned, this MD top, let's say this is the Kato-Nakayama log space. In particular, it gives I want to keep this somehow, but okay, let's erase. So it really gives the topological Milnor fiber because of this. This is already studied by these guys. And so we have one equivalent construction using the so-called maybe deformation to the normal cone or graph construction by McPherson, but in a slightly modified version, so real-oriented. The deformation to the normal cone. So maybe rather in the spirit McPherson graph construction. So this is much more geometric and quite close to the construction of the Motivic Milnor fiber I already erased, given by Guibert-Lozer-Merle. Let's see that close to the construction of Motivic Milnor fiber by Guibert-Lozer. 2006, I think. Yes. So they use this deformation to the normal cone to construct the pieces LGI. So maybe not with this name exactly, but they use a deformation to construct this piece. With this real-oriented version, we are able to do a more geometric global drawing. So let me try to explain a bit this approach. So let me come back to the situation. So we have our non-singular space. We have one divisor on it. And this comes with a line bundle. And one can choose a global section, which gives the divisor as the zero point, zero locus of your section. This Li will have to do with this L capital J. So do this for all of your divisors, and then you will be able to express your function, let's say, as a unit times the product over all the divisors of the section with some power corresponding to the vanishing of the function along the divisor. So this is a unit, yes. So that's the global picture. So pick one of these divisors. Let me try to do the construction, but where there is just one divisor to begin with. So what about this deformation to the normal cone? Let me try to make a drawing. This will be M. we have somewhere the divisor, it will be a point here. We have the line bundle above the point, and of course everywhere else also on M. And so we have a section which vanishes. Let's say the section is something like this. And we are going to push the section somewhere at infinity. Okay? And we do this as follows. So consider m times c star. So we see m in the line bundle. We are going to compactify at infinity the line bundle. So it says projective compactification of the line bundle, and you add some constant bundle. So keep track of C here. So you pick a point, you pick some complex number, and you bring this here into the value of the sections times projective coordinate t, and keep track of t. Yeah, so if say t is 1, so you just have your section. And then if you want to see this in the affine chart, you put t there and you divide by t. And making t go to 0 there, then your section will go to infinity. And let's say that we can project this over C. And so the graph construction is to take the Zariski closure of this inside this set and to look at what happened just above the 0 here, meaning really what happened when t go to 0. So that's the graph construction of deformation to the normal cone. On doing this, I do not maybe write down what it is. I just write the result, so I repeat again maybe. Yes, I t go to 0, so I deform this section to infinity. Here maybe should need some color, so I have compactified this drawing at infinity. And as you can imagine, we are going to obtain some of all of this and all of this. At least that's what suggests the drawing. And so say fact, this construction does give what appears on the drawing, meaning that will be the projectivization of the line bundle restricted to the divisor. So this is this part compactified. Well, this is a line, this is just a point, yes. Plus union, what appears here at infinity, which is exactly the blowing up of m along the divisor. So of course, this is just m, actually. Let me keep it like this. And the union is just, the intersection is above this point, yes. So along the projectivization of L stick to D, something like this. Okay. On M, we have a function, and this function does deform too. So maybe I will not give the expression no, but it is a deformation of this function that will give the map there. But maybe I'll skip at the moment at least this. So this is a classical deformation to the normal cone, but not I want a real oriented version of it. Maybe I will use the same. And use colors. I think it is recorded, yes. So if you forget this, you can go back. So if you want to do the real oriented version, then I will replace this by positive real number. So maybe R like this. And now what you will pick here is not the projective but the sphere bundle obtained from L by adding just positive real numbers here. So of course you have a corresponding class here. So what is the reason to, or maybe just to finish here, you will have the same with this replaced by the sphere bundle, this unit plus. This will be the real oriented blowing up, which will put an over-oriented there, which is no longer isomorphic to M, so here really something happened. And this is the sphere bundle. So let me try to explain this. So what is the real oriented blowing up? Well, if you are in C and you want to blow up, say, the origin, then you replace the directional line by you separate the direction of line, and this will give you C again. But do the same with half line. If you want to separate half line, then you will create some S1, let me write inside, and the remaining of C is there, so say C star, but you have replaced the origin with some S1. So if you have some half line here, it goes here, and some other one right here, is separated. So that's the real oriented blowing up. Let, for us, look at it rather not in C like here, but in, say, P1. Let's say that this is C union infinity, why not? And you do the blowing up of infinity. So if you begin with this and blow up infinity, then you have C. Where is C? Here. Let's say this is C. And so the point at infinity is replaced by one circle. So that's just a compactification of C by S1 at infinity. And essentially, what I have described here is exactly what happened there. Meaning that here you see that your C has been compactified by one point, but you compactify by a circle. So let me make some drawing to illustrate the situation. Should be this page. So I want to keep this. Okay, maybe let me make the drawing there. So you have the ambient space is M there. You have your divisor, and above one point, you have your line bundle. So let me draw now really as something which should look like C. And I compactify this with some S1 at infinity. I do it with all points along D. And so at the beginning you have D which is embedded in M, and after your deformation you have D which is embedded in some tubular neighborhood of D, and M is outside. Yes, what you have now is some new space. Yes, new space. Actually, that's exactly MD complete, which is a full space. M is everywhere around. And you have a tubular neighborhood, but this is really the line bundle you have at the beginning. So this is algebraic structure. So what you have inside is really your line bundle over D, and around you have the boundary of your tubular neighborhood, which give this topological So inside, this is this Li, which is, let's say, if you remove what is in D, and we put a star, and that's exactly this set. So this is if we have only one divisor everywhere. If we have several ones, we'll do the fiber product of this construction. So let me try to explain what we obtain like this. Still 3, 4, 5, 6, 3.5, 4. Okay. So let's say that we have yes. So let's say just first drawing we have D, which is not here. Let's say the light bundle we draw it like this, and at infinity we have this S1. That's a schematic story for that. If you have several ones, then the drawing will be, so this is D1, D2. So picture is the same on the divisor far from the intersection, but at the intersection we no longer have just a line bundle, but the fiber product of two line bundles. So this is C star square now, corresponding to, say, L1 star fiber product L2 star, but above the intersection. One intersected with D2. And we have this S1 bundle. And here we have, as you can see, some torus, so S1 times S1 represented by this part. Actually, by doing this construction, we have moreover some other pieces appearing here, which are not in the Motivic aspect or in the topological, but they are in the middle. And they are very useful for some construction, notably to recover the Motivic, the monodromy, the geometric monodromy on this mode. Let me just finish by this. So the Motivic Milnor fiber was something like this. I explained this, which corresponds to this fiber product over the intersection of the divisor. And look now, how to pass from the white diagram, here by the white drawing, to the red one. Is by taking here some quotient by R plus, yes? As from C star, you pass to S1 by taking the quotient. So we have some geometric way to pass from the this Motivic fibration over the divisor to the topological one by taking some quotient. So one quotient here. In this drawing, we'll have to take quotient by this, the square. And this gives you exactly some interpretation for the sign here. You see that taking the quotient, this is a topological object, this is an algebraic object. If you want to relate this to the topological Milnor fiber, which you can use right as, say, the disjoint sum of the similar model here, but with a sphere bundle. So these are topological objects. You take the union corresponding to this for the fiber. You pass from here to there by taking quotient by this to the power j. And this is in some Grothending ring. And looking at R strictly positive in the Grothending ring, well, one way to look at it is by taking another characteristic, which is -1. So somehow this -1 is explained by this quotient by R to the j. There's still one minus there. But all this story comes with maps, actually. Maps to C star 2. And if you pass from C star to S1, here again you have to do some quotient. And this minus can be interpreted by this quotient by R plus on C star on the target. So, okay, I think I have the end of my time. I have said just one word to finish. I have a complete drawing with some way to pass from one to another, on which gives some hint, at least, on why this formula should be like this. Okay, thank you.
Okay, any questions? Yes?
So you did this now for normal crossing devices.
Mm-hmm.
Is there any hope to do this also directly at a singular level?
Yes, that's for the second talk tonight at 20.
Okay.
So this is a normal crossing. If we change the model, so we have to understand how this diagram changes with the model. We know how it changes. It's a bit technical, but though it's possible to do it. And so really we can understand fully that. In particular, this was page number 7, I think. If we do this, we can obtain that this Motivic Milnor fiber, which was an object in the localized rotating ring, can be defined without localizing, actually. So we don't need to localize. We need to localize it if we define it by the zeta function formula. But doing directly geometry like this, we do not need it, and we can prove that this formula is well defined independently of the model. So this is not a new result. Nikkei's on Payne that I mentioned already proved that using Reshevsky-Kajan Motivic integration. But we recover this by this construction.
So maybe I will repeat my question from the talk. So I already understood the vertical arrows, and lower horizontal are quite clear, but what are the upper horizontal arrows? I think I understand the right one, but what is the left one?
The left one, yes. So this is in the deformation to the normal cone. Yes, let's look at this drawing. This one, I mean the vertical line gives the space on the left. And if you add the two red points, this is the space in the middle. So as you can see, they are included one into the other.
When motive you associate the realizing it?
Yes. If you want to realize it after in the Grothending ring, but somehow we don't work in the Grothending ring. We really work geometrically, but we can recover the Motivic Milnor fiber by adding this sign, as usual. But here somehow it gives one reason to do it. Not just because we have to, but we have some geometric reason why to do.
Good.
It's not much, but this is something.
Yeah. Maybe I have a remark to understand the arrows. It's good to use this log geometry, which was not in the talk, because as he said, everything is factorial.
If there's no more questions, we thank the speaker again.